Okay. Thursday. But what I feel like I left you guys, no, I know I left you guys with a tiny task. So we were talking about calculating what sample size you would need, right? Given some margin of error that you want to be reporting and some confidence level that you want to be reporting at, okay? And so what we said was, okay, well, we can change this formula, right? Where the plus minus chunk is the margin of error, right? And then we can solve for n, okay? So what we said was, okay, well, this is before I've calculated a sample, which means I'm not going to have a sample proportion, right, p hat. So that's kind of a problem, right? And so kind of horse before the carriage type of deal. So we don't have p hat yet, okay? So what we do is we replace p hat with p star and q star. Now we have two options for calculating the sample size. If you have no prior knowledge about the population, so you do not know anything about this population, then you use a 50-50 split. What that's going to do is it's going to maximize the n that you would possibly need, right? That can be very expensive, right? And so it's not always recommended. So what you can do is, if you have any sort of prior knowledge, so from a previous study, so if this is an annual study that you do, right, and maybe you know it's 0.2 and 0.8 or something like that, what you're going to find is that it's a smaller n that's going to be produced, right, which means that it's going to be cheaper to run than just going in blind with a 50-50 split. Okay. And then I left you with this itty bitty exercise that we are going to finish today. So review, we can calculate the sample size this is supposed to say needed, but I'm going to rewrite that. Needed to achieve a desired margin of error at a specified confidence level using, and I'll put that in here, but then I'm going to grab the formula using the sample size formula. Copy. Okay. Yes. Where we have two options for P star, where P star is 0.5, right? No prior knowledge. Or P star is equal to P hat from a previous study. Okay. So now we can do this exercise. And so we have just a little blurb here, exercise 611, which I don't know, presents the result, but I don't think we needed it because I didn't copy it. Presents the results of a poll evaluating support for a generic national health plan in the US in 2019, reporting that 55% of independents are supportive. If we wanted to estimate this number to within 1% with 90% confidence, what would be an appropriate sample size? So, all right, so we want to find n. Let's start there. So n is z star over m. squared times P star Q star. Okay. So in 2019, they did a study and they found that the proportion that were supportive was 0.55. So what we can do is we can use that as our P star, right? Or we can use 0.5 if we assume we have no knowledge, right? If this wasn't included, then we use 0.5 here. We're going to do both just to see how it plays out. Okay? But here, this means that P hat equals 0.55 from a previous study. Within 1% is really saying plus minus 0.01, right? Which means that the margin of error, so therefore M is 0.01. For a 90% confidence level, Z star, you might remember 1.645, but we can grab it from here, right? So a 90% confidence level, Z star is 1.645. So this means that Z star is 1.645. So therefore, P star is 0.55. Now we can plug these values in. We have N is 1.645 divided by 0.01 squared times 0.55 times 1 minus 0.55. I forgot the previous page of my notes, so I'm gonna have to. It's exercise 615, wherever that is. Let's see here. Page 216. Did you find it? So 1.645 divided by 0.01 is 164.5 squared times 0.55 times 0.45. Oops, 45. Let me just confirm that. Okay, yeah. 164.5 squared times 0.55 times 0.45. I get N equal to 6697.411875. Now, one major problem here is that I can't actually sample 0.411875 of a person. Okay, so what if I roll it down, right? If I rounded properly, this would just be 6,697, right? But then if you kind of work backwards, what would happen to your margin of error? Your margin of error would just be slightly bigger than 0.01. Not that that's a huge deal in real life, right? But what we should be aiming for is 6,698. Right, so as a rule, you're always going to round up regardless of the decimal value here. Okay. So here, what I'm going to say is, since we can't sample 0.411875 of a person or an opinion, I guess, we must round up. No, because like I said, that would give you just a slightly, so if you kind of reverse engineer it, your M would end up being just slightly bigger than 0.01. And I mean, not a huge deal at all, but just for kind of being proper reasons, you should round up.
Oh, within 1%, so yeah, we would want to go down.
No, so you have to go up for your sample size, right? Because you increase your sample size to decrease your margin of error is the relationship, right? Just because from, and now I don't have it, but in your confidence interval formula, right? If you increase your N, then because it's in the denominator, then it's going to decrease your margin of error. So then if, so that they have that relationship. So we would need, even though properly rounding would give us 6,697, we actually need 6,698. And we always round up, even if this was 002 or something like that, you're always going to round up, because what's the harm, right? And you just want to make sure that you're getting that sample size. So this was with this prior knowledge, right? How would the sample size that we would need change if we didn't have that prior knowledge, right? We said, okay, well, if I don't know anything, then I'm gonna kind of optimize the N, or not optimize, but maximize. Okay. So what if we had no prior knowledge? About P hat, then we're going to use P star equal to 0.5, right? So the only thing that changes in our formula is N is Z star divided by M, square that times P star times Q star. 1.645, right? The confidence level is going to stay the same. The desired margin of error stays the same, but I'm going to change it to 0.5, and 1 minus 0.5. So I get 1.645 divided by 0.01, square that, times 0.5 times 0.5. 6,765.0625. So even though this is small, right, you still have to round up. Kind of counterintuitive initially, but you kind of think about it, how it relates to M, then it's not too bad, right? 6,766. Right. Which, how does that compare to the original, right? It's, let me see if I'll just copy this so I don't have to remember it. Copy. Versus right, so slightly larger, or quite a bit larger if it's expensive to sample people, right? Then having that prior knowledge saves us a little bit of money, right? And time, obviously. Trying to get these opinions is hard, right? And so, but if you don't have any knowledge, right, this will give you, so notice using P star equal to 0.5 gives the maximized value.
So it's always good to have something from a previous.
Yeah, it's definitely cheaper, but if you want kind of like the highest number of people that we would possibly need to sample, then you would use the 0.5. And when I worked at the market research firm, a lot of them came from like kind of social sciences backgrounds. So their stats, so I was kind of like the statistician there, and then they came from other backgrounds, but they had these cute little wheels that you would adjust the margin of error and that you wanted and the confidence level that you wanted. And then it would just tell you what your sample size had to be. So they had these little wheels that they would bring out, and they're like, oh, what sample size do I need? And I'm like, it's a pretty simple calculation, right? They're like, oh no, I need this wheel. It's like a little paper spinning wheel. So yeah, everyone wants a wheel. Right? Yeah, so pretty cute. But anyways, yeah, so I blew their minds and showed them how to calculate it. Anyways. And now you can too. All right, so great. Are you guys ready for your second question type? Number 2. So far, we've only done one sample proportion types of questions. So this is kind of the end of the review. And because it's a brand new section, I'm going to put it on a fresh page here. 6.2 is the difference of two proportions. I like to classify them as question types, right? Because that'll set you on the right path for what formulas to use and all those kinds of things. And so in terms of the question types, I'm going to call this two sample proportions. Okay. And I call it that because on your formula sheet, right, we've seen one sample proportion, right, so far. Now, if we go to the top here, kind of newspaper style, now we're moving into two sample proportions. And oh my gosh, don't look now. It's terrible. But it's all there to help you, right? And so we'll dissect it. Yeah. So two sample proportions. May as well bring this all in. We'll tackle it one little bit at a time. Two sample proportions is exactly what it sounds like, or like it sounds like. Now you have two samples and you want to compare the proportions from those samples, right? Maybe you have voting information from the West Coast versus the East Coast, for example, right? Or kind of, I don't know, support for people who vote Democrat or Republican, right? So now you've got these two different samples and you want to compare their proportions. Okay? So to compare two proportions to sample proportions, because what were we doing before in one sample proportion? If you only have one sample, then we compare it to some number, right? Is it less than 60%? Is it more than 50%, right? That kind of thing. And so we just compare it to a number. We do the same thing, but now we've got samples for both, which means I have a sample proportion for both of them, right? I have a sample size for both of them, right? And so there's a lot more kind of action. But in general, to compare two sample proportions, okay, we consider the difference in the proportions. We consider the difference in proportions. Like P1 minus P2. So I want to learn about how does the population proportion of group 1, how does it compare to group 2? Okay. Now, we're going to use these group specific subscripts. It doesn't matter which one you use as which group as long as you're consistent. Okay. And I'll make a note of that, but later. So what's your point estimate going to be? Well, if I want to learn about P1 minus P2, then my point estimate is going to be P1 hat minus P2 hat. All right. So first things first, that means our point estimate is P1 hat minus P2 hat. I give you this kind of large looking sampling distribution, right, of P1 hat minus P2 hat. It still follows a normal distribution centered on P1 minus P2, which is what we want. We want to learn about, okay, well, how does P1 minus P2 behave? And then the standard error, we're just going to ignore for now because it's quite large. And it does change a little bit depending on if you want to do a confidence interval or a hypothesis test, right? Which we saw before as well. Okay. All right. So let's start with is this? Okay, a little bit hesitant to bring it in because I kind of had something else in mind, but unlike last time, I'm going to start with the conditions. Okay. So first things first, independence, that condition is, it's always your first condition, right? And so the independence condition is the same, right? Except now you have two samples, so they both have to be randomly sampled, or you have to assume that they were randomly sampled, right? And so if they were randomly sampled, so if the data came from two independent random samples, right, or if they came from a randomized experiment, then you can assume independence. And then we have the added independence condition that, okay, well, within each group, you have to have independence, so they have to be randomly sampled individually, but also that means that we can assume that they're independent of each other as well. Okay. So here, within and between two groups. So within independence, within both groups must be randomly sampled. All right. And then the independence between the groups must be independent of each other. Groups must be independent of each other. So you can't do weird things like take sibling pairs and put them all into, randomly assign each one to group 1 or group 2, because then there's no independence between the groups. But that's so rare that you would even want to do that. So if you've randomly sampled from the populations, then you can assume that there's independence between each group as well. Okay. Now the success failure condition, okay, has to hold for both the groups, right? So both groups have to have a big enough sample size, right? And so depending on if we're doing a confidence interval or a hypothesis test, the success failure condition is going to change slightly, just as it did for one sample proportion. Okay, and so the success failure condition, I'm just going to dive right in and tell you what they are. if you're doing a confidence interval, I'll kind of highlight that here, then you need to check that N1 times P1 hat is greater than or equal to 10. N1 times Q1 hat has to be greater than or equal to 10. And the second sample size also has to satisfy it. N1 times P2 hat, or sorry, N2 times Q2 hat. Both of these have to be greater than or equal to 10. A little bit more work, but not too bad. If you're doing a hypothesis test, all right, I said it, I'm just gonna jump right in. You need N1 times P hat. Now P hat, wait a second, Emily, that makes no sense. I have two different samples. So when we're doing hypothesis testing, what we do is we use this pooled proportion. Okay? So it's going to be N1 times P hat has to be greater than or equal to 10, and N1 times Q hat has to be greater than or equal to 10, where P hat is the pooled proportion. Now the pooled proportion is on your formula sheet. Okay? So it's very large just because I've given you two different ways of calculating Z, and I've told you what proportion is. Okay? Because the hypothesis test or your Z score depends on the pooled proportion. So I'm going to grab from the formula sheet here. So the pooled proportion is when you just, there's this cute image from a textbook at some point that I read where it's someone pushing all these proportions into a pool. And so it's just the number of successes divided by, so the total number of successes over the total sample size, right? Which is, you can even use, or I'll use a different color here. You could even say it's X1 plus X2 over N1 plus N2, right? If you prefer to use X's. Right. So P hat is this pooled proportion that we're going to use, which kind of simplifies things a little bit once you have it under control. So like I said, we're just jumping right in. And then to check the second sample size, we do the same thing. N2 times P hat and N2 times Q hat has to be greater than or equal to 10. Kind of show that those are from there. Well, that's a load off for me. There. That's just a fact. We're just accept it blindly and just go for it. And it's on your formula sheet because it's hard to remember, right? But there, I said it. All right. There's an added caveat that your hypothesis test has to be that P1 minus P2 is equal to 0, your null hypothesis. If you want to test if it's like 0.1 or something, then you don't use the pooled proportion, but we're always going to have it equal to 0. So forget I even said anything. There, it's in the recording, immortalized forever. Okay. So then once you've checked the conditions, right, depending on if you're about to do a confidence interval or a hypothesis test, right, then once you've checked it, or if you're doing both, you may as well check them all, right, all in one go. So I always say you should read the question first and then check the conditions that apply. Right? All right. If these are satisfied, right, when these conditions are satisfied, then the standard error of P1 hat minus P2 hat is going to be P1 times Q1 over N1 plus P2 Q2 over N2, right? But it changes slightly depending on if you're doing a confidence interval or a hypothesis test, which is also on your formula sheet, right? The standard error for a confidence interval, we use that same trick that we did for one sample proportion. Well, if I don't know P1 and P2, then I do know P1 hat and Q1 hat, or P2 hat. So I'm just going to use those. Whereas if I'm doing a hypothesis test, then I have this pooled proportion that I can use. Notice that the only difference between this formula and this formula is that I've distributed the P1 or P hat Q hat over. So whichever one you prefer, here you only have to enter it one. Not a huge difference. Okay, so let's do an example. It's going to be a confidence interval example, I think. Yes. Where is it? There. It's going to be guided practice 6.13, 6.14 here. This one's kind of fun because there's a lot of things that you could talk about. A 5-year experiment was conducted to evaluate the effectiveness of fish oils on reducing cardiovascular events, where each subject was randomized into one of 2 treatment groups. We'll consider heart attack outcomes in these patients. So we've got the fish oil group and we've got the placebo group. We've got the heart attack group and no event, so no heart attack, obviously, and then some total. Okay. So we could talk about the proportion of those who had a heart attack in the placebo group. We can talk about the proportion of those who had a heart attack in the fish oil group. Or on the flip side, if you prefer to focus on non-heart attack event or no events, right, you could do that. But usually we're interested in kind of monitoring heart attacks, right? And so now we're going to be told which group to talk about. So create a 95% confidence interval for the effective fish oils on heart attacks for patients who are well represented by those in the study. So obviously there were kind of study criteria that we're not privy to, but that's fine, right? So if you match the criteria of those in the study, then you will probably fall into kind of this distribution. Also interpret the interval in the context of the study, right? I feel like I shouldn't have to tell you to interpret a confidence interval, but I do. So, because if you make a confidence interval, it's not worth it. All right. So we want to know for the effect of fish oils on heart attacks. Hey, that's green, too dark. Oops. So we've got 2 treatments. Let's just kind of break this down. And we have 2 outcomes. So we want to compare the fish oil group to the placebo group, right, in the heart attack category. That's not super easy to kind of extract from this, right? But you want to compare the treatment groups, right? For so for the effective fish oils on heart attacks. Okay? And so the effective fish oil versus placebo is really what it should probably say to be clear, versus placebo on heart attacks. So I want to denote my groups somehow. Yeah. Well, because you need something to compare it to, right? And so you always need a baseline. So that's why you always need a placebo, right? Or a control group.
Oh, okay.
Yeah. In experiments, you use placebos. If you are kind of doing like exercise studies and stuff like that, you would just have a control group who just, yeah, don't do the knee exercise or whatever. And then you do measurements on them. But in kind of clinical studies like this, if someone is not getting a pill, right, that is going to kind of, well, it's the placebo effect,
Yeah.
right? It's just thinking that you've got a treatment often does a lot of good,
Yeah.
right? And so that's the placebo effect. So you need to have some sort of baseline. Otherwise, these people took fish oil and you have no idea, right? Where would they have been? Or as a group, where would they have been if they hadn't? Not individually, right? We can't say individually, but as a group, we can say, okay, well, this fish oil group actually now has fewer heart attacks, right? Or proportion of heart attacks, which is what we're about to decide. All right, so just to kind of, I'm gonna let FD be the fish oil group and P be the group. Because what I'm going to do is I'm going to use kind of question specific subscripts, which is what I encourage you to do, because otherwise it makes it hard to read. So what I can do is I can find P hat F is 145, because I want to talk about those who had heart attacks. So 145 of the fish oil group had a heart attack over the total, which is 12,933. You want to be careful that you don't use the no event, right? Sometimes you're not given the totals, right? So then you'd have to find the totals. But that's kind of the most common thing I see, is just dividing by the wrong total. This isn't the total, right? That's the total. So then I get P hat F is, and I'm just gonna go in blind from my notes here, 0.01121162917 to 4 decimal places, 0.0112. Right, 4 is usually safe. The sample proportion for the placebo group, there were 200 heart attacks out of 12,938. So 200 divided by 12,938. So P hat P, I get 0.01545. I think there's an extra 1 in here. 0.1545. That feels like plenty, but I'm going to keep going. 833,977, but to 4 decimal places again, 0.0154. Jumping around today. Picky, but approximately equal to. Okay. So what we want to know is 0.0112, is it significantly different from 0.0155? what we learned from the one sample proportion is that, well, it depends on the standard error of this thing, right? So it depends on the spread, right? Just eyeballing it, I'd say they look pretty similar, right? But it depends on what the spread is. So, all right. So what I want to do is first check the conditions, right? The conditions or the assumptions. If you prefer to call them assumptions, that's totally fine. We're asked to create a confidence interval. And so that's all I have to do. So I'm going to check the conditions for a confidence interval, which were independence. That's kind of an easy win because it's always the first condition, independence. It does say each subject was randomized into one of two treatment groups, right? And so subjects were randomized into the treatment groups so here's where I'm just going to force it. I'm going to say, so we may assume independence within and between the groups. So we may assume independence within and between the two groups. Good. The success failure condition is the second condition, and maybe I'll number these 1, 2. There's only 2 conditions. For a confidence interval, I need, and we were given the successes, right? So we may as well just use that. So X1 was 145, which is greater than or equal to 10. Dink. N1 minus X1, which is the number of failures. Now, what's nice is we have the number of failures, right? Failing to have a heart attack, 12,788. Which is also greater than or equal to 10, so that's great. X2, the number of successes in group 2 is 200, which is greater than or equal to 10. So N2 minus X2, the number of failures in the placebo group, 12,738. Which is also greater than or equal to 10. Right. Like I've been saying, all of these conditions will always check out, but that's because these are kind of curated examples, right? But you need to kind of get in the habit of checking them for real life scenarios, right? But if your sample size is large enough, then it'll be satisfied anyways. All right, so therefore, we, and maybe I'll say the conditions for inference are satisfied. At least for a confidence interval, but I'm not too picky there. Okay. So we wanted to build we want a 95% confidence interval. And from your formula sheet, it's going to be built around P1 hat minus P2 hat. And sometimes I throw brackets around there to show that that's a number, right? One number plus minus. It's going to be Z star times the square root of P1 hat Q1 hat over N1 plus P2 hat over N2. Or on your formula sheet, I think it's written the same way. It is. Though it's kind of a large looking formula, it's not too bad, right? If you just kind of think about it as an extension from just one sample proportion, you just do it twice, sort of in the square root. All right, so we have P1 hat, we have P2 hat, we have N1, we have N2. All I really need is Z star. Now Z star for a 95% confidence interval, right? We know how to find that. So Z star from 95% confidence interval, Z star is 1.96. Right? So I still need to move out 1.96 standard errors around my point estimate. And so that idea stays the same. You can see why we started with 1. And so Z star, just because I want to have it here, Z star is 1.960. Want to have it so I can just plug it in on the next line here. All right, so, what did I do? I used 1 and 2 instead of fish oil and placebo. And sure. PF hat minus P hat, wow, that's a lot of P's, plus minus Z star times PF hat QF hat over NF plus P hat QP hat over NP, if you prefer, right? I don't prefer. Or using question-specific subscripts. Same idea though. Oh, this might be a good time to mention it, right? You can use these subscripts. It actually doesn't matter what order you use them in, as long as you're consistent. And even that, it doesn't really matter. It's just as long as you're calculating the difference consistently, right? And interpreting it consistently. I always go however the groups appear, because otherwise I get kind of confused. It's a matter of knowing yourself, I guess. Or if, for example, you don't like negatives, who likes negatives? Nobody. Then you could reverse the order of the difference, right? If you wanted to avoid it, because what are you going to have? 0.0112 minus 0.0155. Just stack this. Plus minus 1.960 times the square root. It's going to be a huge square root here, so I'm going to leave myself some room. 0.0112 times 1 minus 0.0112 divided by n. For the fish oil group, 12,933. Let me see here. Just confirm. Yeah. Plus 0.0155 times 1 minus 0.0155 divided by 12,938. There. That's huge, right? I don't actually need you to write down the steps for the calculation. What I usually do is once I have found this huge square root, because it's usually quicker if you're just doing it in your calculator than pausing and writing down each step. You don't have to do that. But what I do prefer to see is what this square root is times 1.96. It's not a big deal if you skip it, but it's just nice to have some sort of pause.
Maybe with like 1.96 square root and then just like maybe different numbers, so like.
That's okay. Yeah. So I'm gonna do a little bit of work, mostly because when you're going back on this, I want you to have something to check against. So I get the square root of, and in my notes here, I have 8.56 times 10 to the negative 7, because my calculator does that. That's okay, because I'm not going to type these in anyways, right? I'm just kind of going forward with it. 1.179 times 10 to the negative 6. It's really important that you need to keep all decimals. Keep all decimal places. Otherwise, it's going to mess with your standard error, right? We're dealing on such a small scale here, right? Your point estimate and your standard error is usually a lot smaller than your point estimate. So maybe not in this case, but smaller than these 0.0112 and 0.011 or 0.0155. So we're dealing with very small numbers. So you have to keep all those decimal places. So then I'm gonna skip to 1.960 times 0.00142679868. This is, and maybe I'll use a different color, is the standard error of P1 hat minus P2 hat. Right.
You don't actually want the like numbers. Which number system?
I skipped it.
Oh, I felt like we were writing like on this.
Yeah, you can, but you can actually skip, right? You can skip to here if you want. Right, you can skip this step. I just wanted you to have something to check against if you're going back through it, right? But on a quiz or on the quiz, you may skip to here.
But then when we write the two numbers,
Which two numbers do you mean?
well, because it's gonna be plus minus.
Oh yeah, so from here, I want to see all the work. So what the rest is going to look like here is going to be negative 0.043 plus minus, and once I multiply it by 1.96, I get 0.027965252. That I do want to see, because that's your margin of error, right? When you multiply it by 1.96, and then you're going to take negative 0.043 minus the margin of error to get the lower bound. And for the confidence interval, right, an interval, we use interval notation, so round brackets, negative 0.0070965 up to negative 0.00150347. Again, you can just go to 4 decimal places, negative 0.0071 up to negative 0.0015 to 4 decimal places. what's really important to remember here is, well, how negatives behave. I guess we should start there, right? This is in magnitude, it's a larger number because it's negative, it's smaller, right? And so that's kind of confusing, I guess. But what I wanted to say was what we're talking about, right? What we built an interval for is the difference in proportions. Right? So here,
Emily,
yes,
I think the calculation is wrong. The difference should be minus 0.0043.
oh, you're so right.
So I have a very different answer than yours. So
I had that in my notes. I just copied it down wrong. So, but if you get a different number, 0043, and then finally, sorry about that. Let me do one of them. Sorry. Negative 0.0043 minus 0.02796522542. Close enough to the negative 3.123. Looks correct to me. It was just typo here. I was missing a 0. And then I am assuming the other one is okay as well. All right. This is an interval for the difference in proportion, right? So this is the difference in proportion of let's get proper here. Difference in proportion of subjects who had heart attacks in the fish oil group versus placebo group. This is where you need to remind yourself how you subtracted the groups, right? Because a negative is going to mean different things. So you had the fish oil group minus the placebo group. So a negative right here, you've got a consistent negative value. So what that means is the placebo group is consistently higher than the fish oil group, right? Because it's negative. Whereas, right, so here, negative values mean that the placebo group is greater than the fish oil group. That looks like a weird greater than. Versus if you have done the placebo minus the fish oil group, right? Then in that case, a negative value would mean that the fish oil group is larger than the placebo group. So in our case, if you had reversed the subtraction in the beginning for your point estimate, right, then all that would change is that these values would now be positive, right? So would yield a positive interval in this case. Since PP is greater than PF, right? Since this value is consistently larger than the fish oil group. Okay. So it depends on how you found your point estimate, right? That's going to determine the sign of your interval. But so that's why I say you should be consistent, but it doesn't actually matter which way you do it. So now we're going to interpret the interval. Want you to use that same blurb that we introduced before. What I'm going to do is I'm just going to write out the generic blurb and then we're going to fill it in. So we are blank % confident the interval from blank to blank captures. Now that captures, right, is still an important word, right? Captures the true difference, because now we're talking about the difference in proportions. The true, and maybe I won't, maybe I'll just, true is meant to kind of hint at the population. You could replace it with captures the population, blah, 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 right? But what do we have? We built a 95% confidence interval. So we are 95% confident the interval from negative 0.0071 to negative 0.0015 captures the true difference in proportion, difference in proportions of patients who have heart attacks while taking fish oils versus the placebo. Who have heart attacks while taking fish oil versus the placebo. Oops, not a bracket. That last bit, that's hard to kind of come up with, right? Especially because the question wasn't worded in a nice way, but on the quiz, I always make it worded in a nice way so that you can just take it and spin it into a conclusion, right? So here, create a 95% confidence interval for the effect of fish oils, and then I added versus placebo on heart attacks for patients who are well represented by those in the study. I reworded that a little bit in our conclusion, or a lot, actually. Okay. What's another way that you could interpret this interval if you wanted to, right? It's the difference, or what could you say in terms of the placebo relative to the fish oil group, right? The placebo group has 0.0071 or 0.71% higher than, percent higher than the fish oil group, up to 0.15% higher, right? Or 0.0015 higher than the placebo group. Okay, I'm gonna jot that down because or we could use the difference to compare the placebo group to the fish oil group. Maybe I'll do this, start it on a new page. right? Which would look like we are 95% confident the proportion of patients who suffer heart attacks in the, let's say in the placebo group, so in the baseline group, in the placebo group, it doesn't matter, you can do it either way, but you have to be comfortable with what these numbers mean, right? So that's the sticky part, okay? So we're 95% confident that the proportion of patients who suffer heart attacks in the placebo group is between 0.0015 and 0.0071, higher than the fish oil group. I did change a couple of things, right? Instead of saying we're 95% confident that the interval from 0.0015 and 0.0071 captures the proportion of patients who suffer heart attacks in the placebo group. I kind of reworded it a little bit. This requires a level of comfort with what these numbers mean, right? So it's not something I'm expecting, but if you want to kind of take it to that next level, you can, right? And in the end, I think that reading this kind of makes more sense than talking about the difference, right? And so, okay, then this group was higher than the other group, right? Or less than the other group if you prefer that way. Okay? And so what we can do now that we've seen hypothesis testing, we can actually use a confidence interval to do kind of an informal version of hypothesis testing. Okay? And so you can use percentages. When they're really small like this, you want to be really careful that you don't kind of make this 1.5% or something like that. But I kept it as proportion because I didn't want to change the wording too much, but absolutely. So it depends. So like I said, it totally depends on your level of comfort with what these numbers are, but proportions are percentages. So that's totally fine.
Emily.
Nice. Yes.
Can you describe that one more time? We are 95% confident that the proportion of patients who suffer heart attacks in the placebo group is between 0.05 and 0.0071. That means fish oil group is having a fish oil is better than not having it at all, or?
That's right. Yeah.
Okay, thank you.
Yeah, because the placebo group has a slightly higher proportion of heart attacks than the fish oil group. And what I'm about to lead into is that it's consistently higher than 0, right? If there was no difference between these proportions, then the difference would be 0, right? And so we can use confidence intervals. This is in general.
So is the 95% of the center we can like definitively say is like
95%, yeah.
something doesn't feel wrong about that.
Yeah, so nothing's definitive, right? Because in order to be completely 100% confident, your margin of error would need to be huge, right? And so then you lose precision, right? And so in order to get this kind of precise interval, right, that's why we had to restrict it to just 95%. But if you make your interval wider, right, then your confidence level grows because then you've captured more and more of the curve kind of visually.
Well, so like when we're doing like medical studies like this, 95, but we go to the public and say.
Yeah,
"It
so
will decrease your heart attack risk."
yeah, so usually depending on the severity, so fish oil, I mean, who cares? You take a fish oil, great. So 95% is fine, right? If you're telling the public to take this like very risky drug, should probably be a little bit more than 95%, like 99 or something like that. So it depends on kind of what it's all about, right? So, but I mean, fish oils, I think we can all agree is relatively harmless, and it has shown that it decreases heart attacks even ever so slightly, right? And so why not? All right, so then 95 is fine. Yes. Okay, so we can use confidence intervals to conduct, and maybe I'll say in general, because I didn't introduce it in one sample proportion, but we totally can. There's a lot going on with one sample proportion. It's kind of rules everywhere. But we can use confidence intervals to conduct informal hypothesis tests. Because if you've made a 95% confidence interval, right? So CI lower and CI upper, right? Some value here. That's going to be equivalent to, right, 5% left over split evenly amongst the tails, and so 2.5% and 2.5%. Okay, so for example, a 95% confidence interval, I'll just say CI, will yield the same results as a two-sided hypothesis test where alpha is 0.05, right, 5%. Will yield the same results as a two-sided hypothesis test at alpha equals 0.05, right, 5%. So really what you're saying is, well, I'm 95% confident that the population proportion is here, or the difference in population proportions is in this range, right? Or you take that difference in population proportions or the sample proportions, you compare it to 0, and if it's far enough away from 0, right here out in the tails, then you reject H naught, right? Because the p-value is so small. Now we haven't done that, so that's why I'm kind of slurring through it, I guess. But I want to show you how to do kind of an informal hypothesis test. Okay, so confidence intervals will only match two-sided hypothesis tests because of the nature of the interval, right? So if you're trying to match it with a one-sided hypothesis test, it's not going to work unless you make it two-sided. But what happens is, what if we want to know the hypothesis test question would ask something like, is there a significant difference in the proportion of patients who have heart attacks in the fish oil group versus the placebo group? So is there a significant difference in the proportion of patients who suffer heart attacks in the fish oil group versus the placebo group. What I'm going to do is I'm just going to give you the null hypothesis because I only have 1 minute left. And that's going to be the fish oil group, the proportion of the fish, this is an F, I forgot. PF minus P placebo, is it equal to 0? And then I want to know if the alternative P fish oil minus PP is not equal to 0. So what we do is we take this value, is it equal to 0? The difference equal to 0. And on a number line, I like to use it just a number line. Right, I have PF minus PP, and somewhere here I have a difference of 0, but my confidence interval said it was somewhere between negative 0.0071 and, let me just grab this copy. Oh, I guess I'm out of time, but just negative 0.0071, oops, it's a 7, up to negative 0.0015. So I use these round brackets. And how does it relate to 0? Well, since 0 is not in the interval, right? That means I have enough evidence to reject H naught, right? Because it's significantly less than 0 or consistently less than 0. Right. Since H naught, that P equal to 0 is not contained in the interval, we have enough evidence to reject H naught. In favor of HA. Formal hypothesis testing tomorrow. All right, I'll stop this recording here.